So I'm taking the option of making sure I can keep to time. So I'm actually going to
in the next 15 minutes
play the video.
Or so, I will provide an introduction to the SWAN Prosperity Partnership in secure, agile wireless networks, and an example of RF fingerprinting using LoRaWAN as a means of detecting rogue IoT sensor deployments. This is a collaborative project with industry and UK government, with this particular presentation containing contributions from my academic colleagues Manish Nair and Tommaso Capello.
Wireless continues to play a major role in our lives, both commercially and within our personal space, as well as aiding industrial automation. Although cellular systems tend to dominate our thoughts, wireless is a major enabler in global navigation solutions and also connects much of the Internet of Things together. This wireless interface can be subject to cyber attack through jamming, replay, eavesdropping, spoofing, and MAC level protocol attack. This radio frequency or RF open attack surface is the subject of SWAN. We are focusing on this rather than the core network of, say, 5G, because this is protected through encryption and authentication. SWAN is a joint industry academic research program addressing the creation of wireless systems which are both resilient to cyber attack, accidental or induced failures. We are funded through the third call of the UKRI EPSRC Prosperity Partnership Scheme, where over £40 million of government, industry and academic investment was put forward to transform the way people live, work and travel. SWAN itself is one of 6 projects that were funded back in February 2020, and we have overall a £6.1 million budget to support our 5-year research programme. Toshiba Europe, based in Bristol, are the business partner lead, and they are joined by Roke Manor Research and GCHQ, and the University of Bristol is the academic partner. What we are able to do is bring together a large group of engineers from industry, government and academia with valuable commercial insights, in-depth technical knowledge, and we are capable jointly of creating holistic solutions to produce a productive, healthy and resilient connected nation, which is one of the key goals of the Prosperity Partnerships. As I've already mentioned, wireless underpins much of our modern life and society, and this is becoming increasingly vulnerable to cyber attacks or other induced failures, with SWAN aiming to develop wireless systems that are resilient to such threats, thus protecting individuals, businesses and society. So our research programme will identify vulnerabilities in RF interfaces, develop techniques to detect and mitigate against these effects, and it will create enabling technologies that sit alongside software-defined radios, following secure by design principles, building on what we've already seen from the IoT Security Foundation. This will allow us to create more resilient and secure systems for the future. At the outset of SWAN, we defined 4 research challenges. The first of these is to do with threat synthesis and assessment, largely driven by the fact that the vulnerabilities of wireless systems to an RF cyber attack had received very little attention. And obviously for critical infrastructure, the impact of denial of service, manipulation of data and control needs to be understood, as well as the mechanisms of such an attack. So later on we can counteract it. So to help us do this, we took effectively what were called the stride cards, initially developed by IBM for connected computer systems, and applied those to an RF system. And this work was very much driven by Roke, and we have now the Roke RF stride cards, which allow us to align these mechanisms to RF systems. Our second research challenge is RF cyber detection and defence. What we have to really note here is that we need power and cost-effective solutions for monitoring of such systems, because things such as IoT is a very low cost. So as we develop our detection systems, we've also got to think about defence in terms of more resistant to waveforms, much more resistant protocols, and perhaps using enhanced spatial processing techniques to defend our assets through distributed antenna array technology. So to take this research challenge forward, we had to adopt a radio access technique, and we've chosen LoRaWAN. It's something which is being very widely adopted as a low power, long range wireless IoT solution, and is very much driven now by the LoRa Alliance. And at the time of putting this presentation together, there were 156 LoRaWAN network operators across 171 countries. And many of the use cases include applications in critical infrastructure. Also, we've noted that there are a number of studies out there which actually shows that LoRa may be susceptible to jamming attacks, and two example papers are given on this slide. Thus, this made LoRa a very attractive first candidate for us to assess in SWAN. Our third research challenge within SWAN is cyber secure radio design, and effectively identifying the need that RF architectures, transmitter and transceivers, need to be much more resilient to attacks, and also allow us to detect the presence of an adversary who's trying to attack our network. RF transceivers also are needed to support techniques such as dynamic spectrum access to improve the use of spectrum, which is one of the key missions that we're seeing emerging as we approach 6G. And also to be able to support this dynamic spectrum access, we need enhanced frequency agility of the technologies which effectively connect the baseband up through to the antenna and radiate. So just as two illustrations of some of the work we've been doing, we've been looking at enhanced dynamic range low noise amplifiers through the application of a derivative feed forward to improve the third order intercept point. And in terms of PA technology, we've actually been looking at some digital solutions of multiple PAs connected together, operating at different power levels, effectively to give us a digital RF power amplifier, which can offer very high power efficiency. Now for our fourth and final research challenge of secure dynamic spectrum access, where we need to understand the vulnerabilities of sharing protocols if a dynamic spectrum access mechanism is going to be secure and also appropriate for enhancing spectrum utilization below 6 gigs. Also, this goes hand in hand with enhanced transceiver technology, where the receivers are more resilient to adjacent band interference and the transmitting stage is more frequency agile, something that Thomas Capello will pick up on a little bit later on this morning. And also there was a presentation by Simon Wilson in Smart 2021 on Wednesday in the research elevator pitches, where he talked about his more secure dynamic spectrum access to supplement licensed spectrum, and is it worth the mobile network operators investing? So within SWAN, we have a rich mix of theoretical work, simulation work, and also practical test beds. So both at Bristol and at Roke, we have an RF penetration testing facility where we've got screened enclosures where we can subject various candidate technologies to cyber attack. And with the Bristol system, we can actually capture the RF over-the-air waveforms and actually convert them back into an IQ format for further processing and fingerprinting. This is complemented by a rollout in the Clifton campus at the University of Bristol of LoRaWAN technology. we've got 3 sites where we've deployed access points, shown here in blue, with the one on the physics building actually having a twin access point technology on plus or minus 45 degrees polarization, so we can also study that. And we've got, getting on towards 20 deployment of sensors around the city in static locations, and then using another 5 or so devices in terms of mobile deployment, so we can actually track what happens in such systems and to see if the observed SNR is a good indicator that we've got a valid node or a rogue deployment has taken place. What I'm going to do now is focus on the IQ capture and using that for RF fingerprinting. So in the Bristol RF penetration testbed, we've taken multiple SODAC LoRa modules and actually subjected them to various forms of jamming attack, and also capturing their waveforms over the air to see if we can do some form of RF fingerprinting on the recovered IQ data that you can see just one example here. So clearly you can go from that and you can look at that in the frequency domain in terms of the spectral content, and you can drill in a little bit more deeper and actually look at the chirp spectrum nature of the LoRa transmission format that you can see here. And you can clearly identify the preamble where you've got the up chirps followed by the frame synchronization. Then you've got the start of frame delimiter before you've got your packet transmission through the network. But what we're actually interested in is to see if we capture these for some different modules, can we identify any differences?
So we can see here some captured IQ data. We'll have a look at this segment here. You can clearly see the constant envelope modulation, or the constant amplitude, due to a continuous wave spread spectrum chirp, and here you can actually see the start of that particular chirp sequence for this particular segment. If we then take a series of segments, we can also plot those. Again, you can see the constant envelope modulation and the rotation due to carrier frequency offset, giving a unique characteristic for this particular device. So we need to then drill in a little bit further and see if this is a good marker in terms of identifying LoRaWAN individual sensors that are deployed in a network.
So we've captured these traces for 5 different SODAC LoRa modules, and also using our Rodent Sports ARB, which we can actually get that to completely emulate the operation of a LoRaWAN sensor. So from these 6 traces that you can see here on the screen, which are all unique in the way that each of the modules start up, we wanted to see if we could do some RF fingerprinting through the application of neural networks to see if we can actually cluster these outcomes in terms of differential traces, so we can identify each of the 6 units that we've been evaluating on our testbed. So we take our captured IQ data for each of the units under evaluation, and we feed that through our neural network, so we can do this differential constellation identification. And what we've found is that we can generate some 2D self-organizing feature maps, and these feature maps, as you can see in the illustration here, is actually different for each of the 6 devices that we've put through the testing. And so far we have found this to be a repeatable marker to identify which unit is transmitting, and with this could take us on then to effectively identify any rogue devices which have been placed into the network if we've already fingerprinted the set which should be valid. So what we're currently doing is looking at enhancing this classification based on convolutional neural networks, and what we're expecting now is to find that this technique is very robust and completely independent of any form of max spoofing that might actually occur in the network. So this is the way we're thinking of taking this forward. And what we will also have to consider is the way that we might actually deploy this on to a network, given that it being low cost and low power is one of our driving features in terms of SWAN's solution. So potentially making the use of edge computing and sharing this fingerprinting technology or methodology from a central location and sharing that out with multiple devices. That, I'm afraid, brings me to a point where I need to stop, given the time constraints with us today. If you're interested in more, please visit the SWAN website or sign up to our quarterly newsletter through this QR code that's currently shown on the screen. And I'm happy to answer some questions on this work that we're doing through the Prosperity Partnership called SWAN. Okay, so folks, you're going to have to help me with some questions. Rather difficult to ask myself questions. So, from fellow panelists, you can unmute yourselves and directly ask me, and our audience, please type into the Q&A box. So David Butler from the BBC has just asked me about triangulating the attack. I suppose there is some possibility of doing this, but it's going to require making the sensor gate, the actual gateways, more complex. The way LoRa works traditionally, you would only receive a sensor at one particular gateway. Ideally, if we could see it coming in from multiple gateways, that would give us some useful information in terms of the bearing. We can easily get observed signal strength, but obviously that's hampered by fading and shadowing in the network in terms of doing ranging. There's no implicit any time-connected networks in there. So a little bit difficult, but I think there are ways we could do it. It depends if it's worth it. I can see that you might want to seek and remove a rogue LoRaWAN sensor, but knowing that there has been infiltration, that sensor is bad, it's probably best to mark it as a rogue and don't use its network. Right, so this is a question that I'm probably not the best person to answer, but is there a way of integrating LoRaWAN with 5G and other networks? I don't know if anybody from the Smart Internet Lab could jump in here in terms of have we actually looked at an IoT system and integrating that across. Alex, can you say a few words?
Yeah, I can brainstorm on that. I think it depends on what exactly is the reason we want to integrate LoRaWAN networks with 5G, because the bandwidth and the speed of LoRa is not really that challenging for 5G. However, if we wanted to integrate it, it would have been we would have to use some kind of hardware that translates the LoRa traffic to 5G. So it is possible. However, we need to figure out why we want to do that in the first place.
Yeah, so there is, you're absolutely right, Alex. The data rate is very, very low off LoRaWAN, but there are many instrumentation and automation problems that would have low data rate sensors, which make LoRaWAN
very appropriate, but there could be another part of the plant or system you're controlling which need the higher rate capabilities of 5G. So actually bringing them together in a seamless architecture would be really good. A bit like the work we did in Toucan, really.
Yeah, exactly. I wouldn't see it as a massive challenge, especially with multi-access edge computing and software platforms that are accommodating heterogeneous IoT networks such as LoRa and BIoT and other technologies. So if there is a use case for it and it's a requirement, I think it could be quite possible. And yeah.
So there's an interesting question from Roger Green in terms of it, effectively the impact of the channel being location dependent. One of the things that we are thinking about, so LoRa sensors are normally static, so you could actually fingerprint the composite device, antenna and channel together. So that would be a very, very good marker of this is device 99. This is what its antenna looks like. This is the channel that we see. And if somebody tries to spoof that from a different part somewhere in Bristol, their channel is different, their antenna will be facing a different way. And the whole way that the modem generates this chirp sequence, the way that it starts up will be different. So the composite channel response is a thing, Roger, that we could possibly use. We haven't done it yet. And just to finish off, Maria, you asked me about the benefits of the Prosperity Partnership versus other programs. So I think one of the real benefits is that our partners, Toshiba, Roke Manor and GCHQ, the engineering staff are working with us on the project. So it's not just the university servicing the activity and getting guidance from industry and government. It actually includes true collaborative work, which is quite a nice way of doing it for something which isn't within an EPSA framework. So at that, I better stop on questions for the first paper, and now move to our second presentation. So